So in the previous videos, we talked about how, different sorts of equations of state help relate pressure, volume, and temperature to one another. It turns out that the equations of state are not only useful for describing those properties, but they're also useful for describing heat capacities as well. So heat capacities themselves can be modeled using equations of state. Okay. All right, and so now that I bring that up, it does motivate the discussion that we're going to have now, which is that when we previously talked about the constant volume heat capacity or the constant pressure heat capacity, when we talked about it in MEB1 or at the beginning of this course, we actually made an implicit assumption every time we used them, okay? And that's because the heat capacities that we talked about before were actually only valid for ideal gases. Okay? So far, only valid at ideal gas conditions. Okay? Alright, and so for ideal gas conditions, that means that your system is at low pressure or at very large volume and temperature. Okay? Alright, and so the CV and the CP that we talked about previously are only valid at those conditions. Alright, and if you're not at those conditions, then your heat capacities actually have different values. Right? And the reason for that is because the constant volume heat capacity, like if we just focus on that first, the constant volume heat capacity actually itself has a volume dependence, even though it's for a constant volume system. Okay? So despite its name, CV actually has a volume dependence. And so to demonstrate this to you, what I want to do is I want to take your constant volume heat capacity, and then I want to take the partial derivative of it with respect to volume. And we're going to hold it at constant temperature. Right? Now we know that based on the definition of a constant volume heat capacity, that it's actually just du dt at constant volume, right? That's where the constant volume heat capacity comes from. And so what we're doing is we're taking the partial derivative of that derivative at constant temperature. Okay? All right, and so starting from here, you could go through all your tools of the calculus of thermodynamics. So calc, or thermocalc, I'll say. And if you go through all those steps, what you could eventually show is that the partial derivative of the heat capacity with respect to volume at constant temperature ends up just being equal to T times the second partial derivative of pressure with respect to temperature at constant volume. Okay? Right? And so we do see here that the volume dependence of the heat capacity, if we had some sort of equation of state here, we could plug that in. Could plug EOS in. We would take that equation of state, then we would take the equation of state would be pressure is equal to whatever. Then we would just take the second derivative of that equation of state, multiply it by T, and then that would give us the volume dependence of the constant volume heat capacity. Okay? Right, so the constant volume heat capacity is affected by volume. And similarly, our constant pressure heat capacity is also affected by pressure. And so in this case, what you could show is that dCp dP at constant temperature is equal to negative temperature and the second derivative of dV with respect to temperature at constant pressure. Okay? Alright, and so once again, if you had an equation of state in terms of volume, you would take the second derivative of it with respect to temperature, multiplied by T, and the negative sign, and then you would get the pressure dependence of Cp. Okay? And so using the calculus of thermodynamics, this demonstrates, that Cv and Cp do have volume and pressure dependencies. Okay? So this is one way to show it. But perhaps a more concrete way of showing it is I could actually just calculate some numbers for you. Okay? And so these dependencies can also be demonstrated using steam table data. Okay? Alright, and so, if we go to the steam tables, or just in general, I guess before I say that, let's say we have the specific heat capacity, right? Heat capacity per kilogram. By definition, we know that this is just equal to the partial derivative of the specific enthalpy with respect to temperature at constant pressure. Okay? So we have these partial derivatives here. But what we could do is we could approximate these partial derivatives as the change in specific enthalpy over some delta T held at a, constant pressure. Right? And so what we could do is if we went to the steam tables and we just looked up at a pressure of 0.1 bar, the specific enthalpy of steam, superheated steam, at 400 degrees, and then looked up the value at 300 degrees, and then divided that by the temperature difference. Okay? From the steam tables, for P is equal to 0.1 bar, we could look up those specific enthalpy values. And we would find that we get a value of 2.032 kilojoules per kilogram per Celsius. Okay? Right, so this is kind of one way to roughly approximate the heat capacity. Okay? All right, so now that I've demonstrated, here's just an example calculation. What I want to do is I want to kind of repeat this calculation not only for different temperature ranges, but also at different pressures. And so I'm going to prepare a table where the first column corresponds to different temperature delta T's. So 400 to 300, 600 to 500, and also 800 to 700. Okay? So that's that first column. And then the subsequent columns are going to correspond to different pressures. So 0.1 bar, then 10 bar, and then 50 bar. Okay? And then I'm going to populate this table by calculating the effective heat capacities for each of these different temperatures and pressures. Okay? All right. And so if we just stick to 0.1 bar and we look at the different delta T's, I showed you earlier that for 400 to 300, the CP is 2.032. But if we look at a range of 600 to 500, 600 minus 500, we get 2.166. And if we go to 800 minus 700, we get 2.307. All right, and so here we see that the heat capacity changes as we change our temperature range, right? That's not surprising. This is what we've seen before, right? We've actually seen that our heat capacity does change as a function of temperature. Okay. All right, but what I want to do now, we did this at a pressure of 0.1 bar, which is a fairly low pressure. What I want to do now is let's bump up the pressure to 10 bar. Okay? And if we do this calculation, we see that our CP, not only increases as we increase temperature, but if we compare across pressures, we also see that the numbers are slightly different, right? And they actually kind of increase as we increase the pressure. All right, so we went from 0.1 bar to 10 bar. Let's now go from 10 bar to 50 bar. And when we do this calculation again, we see not only do the CPs, effective CPs, increase as we increase pressure, but now the trend that we see across temperature, is different. We start off very high here, but then as we increase temperature, we go to a lower value and then to a higher value. Okay? And so what we end up here is we see a nonlinear relationship with temperature. Okay? All right, and so I kind of went through this exercise because I wanted to demonstrate to you, that it's clear that our constant pressure heat capacity is affected by changes in pressure, right? And so with an ideal gas, we wouldn't expect to see this. But when we take real data from steam, from the steam tables, we do see this effect in play. Okay? All right? And so to end this video, I just want to say that, to at least kind of comprehend these non-idealities with the constant volume and constant pressure heat capacity. So previously we used steam table data in order to account for that. But let's say we want to work with a different chemical that wasn't water, like we wanted to work with like nitrogen or something, or we don't easily have nitrogen tables on hand. So I'll say that if you don't have any data, if you wanted to account for non-idealities, in CV and CP, one approach would be to rewrite CV and CP like this. And so if we think of molar constant volume heat capacity, so this is the total molar constant volume heat capacity, what we could do is we could split it up into two terms. The first term would be what I call the ideal gas heat capacity. So this would correspond to a volume of infinity, and the star here just means ideal gas. Okay? In any case, we take the ideal gas heat capacity and we add onto it a term that accounts for non-ideal behavior. And so here's that where that second derivative of pressure with respect to temperature, here's where that would come into play. And we do the same thing for CP as well, where we have an ideal gas term where pressure is taken at the limit of 0. And here we're going to subtract off the non-ideality. So it's the second derivative of volume with respect to temperature at constant P. Okay? And so I want to emphasize that these terms at the beginning here these are the heat capacity values for ideal gases. Okay? And for an ideal gas, these things are only a function of temperature.